Alright, so thermochemistry is the chemistry that has to do with heat. Chemistry that has to do with heat. Okay, that is basically thermochemistry. Now, just something that I can be able to mention is that when you are talking about thermochemistry, we have got different types of heat when you are talking about thermochemistry. The first heat I should mention is the heat of the reaction. Heat of reaction. This one I'm going to give it as delta H with R to mean reaction. So the heat of the reaction, when a chemical reaction is happening, you can have the reaction taking in heat or losing heat for it to occur. Let's say you have got X plus Y, and this is going to, let's say, XY. So the heat of a reaction delta HR is going to be given as the sum of the heats on the product minus the sum of the heats on the reactant. That is going to give you the heat of the reaction. So it can either be the heat gained or the heat lost for a reaction in a chemical reaction, because a reaction sometimes can be endothermic or sometimes it can be exothermic. You also have what we call the heat of formation. So again, we'll give it as delta H to put F. So if this one is happening at standard conditions, you are going to see a zero on top. That is a heat of formation at the standard heat of formation. So let's say we have got aluminium, which is reacting with oxygen to form bauxite, aluminium oxide. If we get to balance this reaction, we can first balance the oxygen by putting a 2 here and then a 3 here, then we'll balance the aluminium by putting a 4 there. So the heat of formation of this reaction is going to be given by the summation of the heats of the product minus the summation of the heats of the reactant. Now, when you're talking about a pure element or a molecule, like a molecule that is the same, like of the same atom, like oxygen molecule, nitrogen molecule, the heat of formation of this is zero. Like a pure element or a molecule which is made up of the same atoms, heat of formation is zero. But for a molecule like ammonia made from different atoms, the heat of formation will be given. So please just take note, the heat of formation of pure elements is zero. So if you get to find delta F to be negative, meaning that in that reaction the heat is released. What does it also teach us? It teaches that the heat of the product is smaller than the heat of the reactants. That is why the reaction gets to give us a heat of formation to be negative. You have got different heats. You have got the heat of combustion. So if I'm talking about heat of combustion, this has to do with it. Now take note of this. When you're talking of heat of formation, heat of what? It should be one more of this substance being formed. Please take note of that. So meaning that in this case where we have got a 2, when you're talking about the heat of formation, you're talking about one more of a compound being formed. So make sure that even when you're balancing the reaction, you should have one more of product. Actually, the values which are going to be given, if they've given you already an equation, just use it like that. But heat of formation by definition is the heat which is either released or gained for formation of one more of a compound. You have got heat of combustion. It is the heat that is either released or gained when one more of a substance burns in oxygen or is broken down. You know that organic compounds, when they react with oxygen, they get to form carbon dioxide and water. So when one more of this compound is broken, that heat which is required is called the heat of combustion, because it has been burnt with oxygen. You have got a heat of precipitation. It's a heat which is either gained or lost for one more of a precipitate to be formed. So one more is very important. So also take note of the state symbols. It's going to be a solid aluminium reacting with a gaseous oxygen and then forming solid aluminium oxide. I've seen some questions where they will just bring this in multiple choice and then they put wrong state symbols to say identify the heat of formation. And they also put a coefficient here. For it to be heat of formation, make sure that the coefficient of what is being formed is 1. For this to be heat of combustion, make sure that the coefficient of what has been burnt is 1. Right? We have got a heat of displacement. That is a heat that is either released or gained for one more of an element to be displaced. Let's say we are reacting hydrochloric acid with, let's say, sodium. The hydrogen is going to be displaced. So one more of hydrogen should be displaced. You have got heat of neutralization and all of those. So you are just talking about one more of something. Right. Now, you have got the measurements of heat. So measurement of heat is called calorimetry. That is the measurements of heat. Meaning that the instrument that you are going to be able to measure, to use to measure heat is going to be called a calorimeter. The process itself of getting to measure heat is calorimetry. Now basically you are talking about the heat which is involved in a chemical reaction. So when you are talking about a reaction, you are going to have the environment and the system. Environment and the system. So for chemical reaction, the system is the reaction itself, the sodium reacting with the chlorine to produce sodium chloride. This is going to be referred to as a system. Anything else which is surrounding the reaction is called the environment. The cup in which the reaction is happening and the outside, this is going to be called the environment of the reaction. Let me pause a bit. Are we going together? Are we moving together? Okay. So from here, when you get to measure this heat, the heat in this kind of reaction, it can either be gained or lost. Now let's say we have got sodium chloride, that is table salt, and this thing you are trying to dissolve it in this kind of reaction. Now also, if you get to dissolve this in water, the water will still be an environment because it's not a point of interest. Our point of interest is the sodium chloride itself. So let's say when the sodium chloride gets to break into sodium ion and chlorine ion, and it gets to release energy. If this releases energy, meaning that the enthalpy of the reaction is going to be negative, then this reaction is releasing energy. And that energy is basically heat. So the same heat which is lost will show a negative to mean lost by the sodium chloride. Then I'm going to say the heat lost by the reaction is going to be the same heat which is going to be gained by the water. So this is from the law of conservation of energy. Energy cannot be gained or made. It can just be transformed from one form to the other. Right? So take note of that equation. It is a very, very important equation. But as you get to talk about also calorimetry, you have got different types of heat. I was mentioning the types of heat of reaction, but we also have what we call heat capacity. So heat capacity is just the amount of heat which is required to raise the temperature of a substance by 1 degree Celsius. Let's say you have got a substance which is at 26 degrees Celsius. Now you want to raise it from being at 26 degrees Celsius to 27 degrees Celsius. You see, we have raised it by 1 degree. So that amount of heat energy that you require for you to raise the the amount of heat energy that you require to raise the temperature of a substance by 1 degree Celsius or by 1 Kelvin is what you call heat capacity. So if I put the word specific in front to give specific heat capacity, that will be the amount of heat energy that is required to raise 1 gram. In some books you say 1 kg, 1 gram of a substance by 1 degree Celsius. So if I put the word specific, then I'm talking about 1 gram. I've specified the mass. So specific heat capacity is given by, so I'm going to use, I'll give the equation for energy. Heat is going to be given by mass multiplied by specific heat capacity multiplied by the change in temperature. This is the equation. But if it is just heat capacity itself, you might not see mass there because we're just talking about the amount of heat energy that is required to change the temperature. You are not interested in the mass. But specific heat capacity also include the mass. Okay, so if I'm supposed to make C, which is a specific capacity subject to the formula, we're going to say it is heat over mass times change in temperature. So therefore, specific heat capacity is going to be measured by heat is given in joules, mass is in kg, and then the temperature can either be in Kelvin or degrees Celsius, and all those. But the mass can also be sometimes in grams, depending with circumstance. We also have what we call latent heat. Now, when you're talking about latent heat is simply the amount of heat which is either absorbed or released during a change of state. So latent means hidden. It is hidden because you'll not be able to see. Actually, what happens during a change of state is that you are going to see the diagram become like this. I'll show one diagram. We'll see a change of state. The diagram becomes like this, meaning that you can't see that the temperature is rising. The temperature doesn't rise at a change of state. That is why we call it a latent heat. So the heat which is required for a change of state to happen. So I've got the latent heat of fusion and the latent heat of vaporization. Now when you're talking about the latent heat of fusion, just like heat capacity, you also have specific latent heat of fusion. If I put specific, then I'm specifying 1 gram. So latent heat of fusion is the amount of heat energy that is required to make, remember this is fusion, alright, to make a solid become liquid or a liquid become solid. Either liquid to solid or solid to liquid. Now if you are talking about liquid to solid, then you are going to say latent heat of fusion is the amount of heat energy which is lost to change a liquid to solid at constant temperature. Please, temperature is constant. So here we're going to say gained because, lost, because when you're changing a liquid to a solid, heat is lost. But if you're talking about solid to liquid, then you're going to say the heat which is absorbed to change a solid to a liquid at constant temperature. So it is given by latent heat of fusion. The energy is going to be given by mass multiplied by latent heat of fusion. In some books we are going to see delta H with the F. So that will be latent heat of fusion. So latent heat of vaporization is the same, but you just put M, delta H, you put a V because that is vaporization. Now latent heat of vaporization, to vaporize it has to involve a liquid and a gas. Fusion has to involve a solid and a liquid. So to move from a liquid to a gas, what you do is apply energy. So latent heat of fusion is the amount of heat energy required for a liquid to change into a gas at constant temperature, or the heat released for a gas to change into a liquid at constant temperature. So these are the different forms of heat that we are able to talk about on here. Okay, we can do some bit of calculation. Now, before I go to some calculation, is this okay so far? Are we good? Okay. Now, let's say we have got 80 grams of water. You want to raise the temperature of 80 grams of water from, let's say, 26 degrees Celsius to 48 degrees Celsius. Okay. How much heat do you need? Now, the specific heat capacity for water is, this is a constant, 4.184 joule per gram degree Celsius. So what is the heat energy that is required for this to happen? So heat is going to be given by mass multiplied by specific capacity multiplied by the change in temperature. So the mass of water given is 80 grams. I'm going to use the grams because I can see the specific heat capacity is also given in grams. So make sure that the units are balancing. And then we'll multiply by 4.184 joule per gram degree Celsius. And then we'll multiply change in temperature. We'll subtract the final minus the initial 48 minus 26. This is going to be in degrees Celsius. So it's degrees Celsius cancels with the degrees Celsius, the gram cancels with the gram. So then the answer, if we do the multiplication, will be 7,363.8 joules. So that is the heat that is required for you to raise the temperature of water from 26 to 48. You can see that it is positive because you have to raise the temperature, but if the temperature is dropping, it would be negative because you are going to be losing heat energy. Okay. Let's say we have got 70 grams of a metal. Okay, you have got 70 grams of a metal, let's say 70 grams of aluminium, and this one is at 180 degrees Celsius. Okay, now you get to drop it in a bucket of water, and the water there is, let's say I've got 400 grams of water, and the water is at 25 degrees Celsius. So, and when these come together, when these two come together, you find that the final temperature, okay, the final temperature of these two is let's say they go at 28 degrees Celsius. What is going to be the specific heat capacity for aluminium? We already know the specific heat capacity for water. This is 4.184 joule per gram degree Celsius. So what is going to be the specific heat capacity for aluminium? So to do that, look at this. Aluminium is hot. Water is not hot. It is at room temperature. So when you drop something that is hot into something that is cold, the cold thing, the temperature rises, the hot thing, the temperature drops. So that is why you see the temperature, the final temperature is 28. This is the uniform temperature. Remember, the aluminium is going to be in the water. So they are going to share the same temperature. So the same heat which is going to be lost by aluminium is going to be the same heat which is going to be gained by the water from the conservation of energy. So the heat which is lost by the aluminium, how do you find that? Is given by, I'll put a negative mass, specific heat capacity multiplied by the change in temperature. And that will be equal to, with the other side for water, that will be positive mass, specific heat capacity multiplied by change in temperature. Remember, the other side is for water. So you can now replace the values. The mass for aluminium, that is 70 grams. Specific heat capacity, that is what we don't know. And then change in temperature. The final temperature is 28. The initial is 180. It says in degrees Celsius, we know that. And that is going to be got now the mass of the water, that is 400 grams. And then multiplied by specific capacity 4.184 joule per gram degree Celsius. Then multiplied by the change in temperature. The final temperature is still 28, but water was at 25. This is in degrees Celsius. So the degree Celsius will cancel, the gram of water also cancels. Okay. So I want to remain with C, meaning that I'm going to multiply the 400 by 4.184, and then I multiply 28 minus 5, that is a 3. Then I'll divide by negative 70, which is in grams. Remember, on top, the only unit that has remained is a joule. And then down, 28 minus 180. That is going to give us negative 152. This is in degrees Celsius. You know that the final answer is going to be this negative, and this negative will cancel. It gives us positive. So it will be in joule per gram degree Celsius. So if we get to punch this, we're going to get about 0.472 joule per gram degree Celsius. So that is going to be the answer for this one. Are we okay? Are we good?
Yes.
Okay. So using the same procedure, we can as well determine the final temperature. Let's give an example. Let's say you have got 100 grams of iron, and this one has got a specific heat capacity of 0.453 joules per gram degree Celsius. Okay, and this iron is at 95 degrees Celsius. You get now to place it in 200 grams of water. We know the specific heat capacity is 4.184 joule per gram degree Celsius. And let's say the water is at room temperature, 25 degrees Celsius. Now you want to find what will be the final temperature when you get to mix these. What will be the final temperature? So the same formula. Negative heat for iron, because the iron is hot, is going to be positive heat for the water. So this is given by negative mc delta T. That will be equal to mc delta T. So that will be negative. The mass for the iron is 100 grams. Make sure that the units are balancing. The specific capacity is 0.45. The change in temperature. The final temperature, I don't know. The initial temperature is 95 for iron. And this should be equal to mass for water is 200. The specific heat capacity is 4.184. And then change in temperature, remember, is final minus initial. The final temperature, I don't know. The initial temperature is for water is 25. So from here, I can divide by negative 100 multiplied by 0.45. Also the other side, I can divide by negative 100 multiplied by 0.45. So these two are going to cancel. So I'm going to remain with T final minus 95. That is going to be equal to, the 100 can go into there, that is 2 times. So that will be negative, this negative now times 0.45, that will be negative 0.45. So I'll multiply first 2 multiplied by 4.184. Then the answer, I'm going to divide by the negative 0.45. Okay, that is going to give me about negative 18.596, and this is multiplied by T final minus 28. I'll distribute the negative 18.5, so I'm going to have T final minus 95 being equal to the negative value multiplied by T final, that will be negative 18.5 960 final. Then the negative by the negative 28, so that will be positive. And that is going to give us about 520.676. So I'll take like terms to the same side. So I'll take this value the other side, I'll take 95 the other side. So I'll start with the 95, it will become positive. It will add to the 520. So 520 plus 95, that is going to give us 615.6755. Of course, it's supposed to be 6 if I run to round off. Then if this value goes inside, T final plus 18.59, so that is going to be 19.596 T final. So to remain with the final temperature, divide the 615.676 by 19.59555506 if you round off. So this is going to give us a temperature of 31.4 degrees Celsius. So in case of punch strongly, then we can revisit that. But that is the procedure that we're going to take to be able to calculate the temperature here. Is that okay?
Yeah, it is.
Okay. All right. Now
The final temperature is really the same for all the reactions.
yes, since you have got iron which is immersed in water, the final temperature then is going to be the same. Like they are all together.
Okay, so are there instances where the final temperature is different with the water, or once it is dipped in water, the final temperature is always the same?
It will always be the same as long as you've allowed them to equalize. You get that? Is there anything more?
Yes.
Okay. So in case of anything, you can go on and ask. All right. Now let me look at one more example. Let's say you have got ice which is at negative 20 degrees. Okay, this is ice. It is at negative 20 degrees Celsius. Now you want to convert it to steam, which is a gas at 250 degrees Celsius. So the question is how? How are you able to convert ice at this temperature to steam at that temperature? Okay. So when you get to look at, because this basically we are talking about is water, we can write, because we are starting with ice, so what we are going to be able to write is a heating curve, because if you have got ice, for you to go to that temperature, then you need to heat it. So this side we are going to have energy, on the x-axis we are going to have reaction progress. So to move from negative 20 degrees, you need first to convert the ice from negative 20 to ice at 0 degrees, because you know that 0, that is where the melting point gets to happen. Okay, so this is going to require heat. Let me call it Q1. When you reach at 0 degrees, a change of state will start happening. You are going to be converting now the ice to water. So when a change of state is happening, you need also energy there. That is latent heat. Okay, latent heat of fusion. And then when that happens, when the whole ice is converted to water, the temperature will start increasing. Now you'll be converting to gas. So when you reach at 100 degrees, the temperature will stop changing, because of course to raise the temperature you need specific heat capacity to raise the temperature from 0 of water to 100. When you reach at 100, the change of state is going to be happening to change the water to steam, and you still need energy there, which is latent heat of vaporization. And then when you've converted all of it now to steam, you can now raise the temperature of the steam from 100 to 250 degrees, and energy is going to be required, which is specific heat capacity, to do that. So these are the energies that you need to calculate, and then you get to sum them up to give you the total energy that is required for you to convert ice at negative 20 to steam at 250 degrees. So to calculate Q1, because we're talking about raising temperature, that will be given by specific heat capacity, that is MC delta T. So the mass, let's say the mass of the water that we have is 24 grams, the mass of the ice. So we are going to use 24 multiplied by specific capacity for ice. Now here, remember, you are using for ice because you still have ice. The specific heat capacity for ice is 2.03. Okay, now you find the change in temperature. The final temperature is 0 minus the initial temperature is negative 20. So 0 minus negative 20 will give you positive 20. So if you do the multiplication, you are going to get about 974.4 joules. And then now you need to find the second energy. Now this is latent heat because you are converting something. That is latent heat of fusion. So that is given by mass multiplied by latent heat of fusion, which I can also mass times delta H fusion. So mass does not change, it is still the same 24. Then multiplied by the heat of fusion. Now what do you have here? You have ice. So you are looking for the heat of fusion of ice at that point, and that is 334. Okay, so if you do the multiplication here, you are going to get 8016 joules. And then Q3 is the latent heat again, because you are raising the temperature, MC delta T, but there what you have is water. So we are going to use the latent heat of water. The mass is still 24, the latent heat of water is 4.184. The change in temperature moving from 0 to 100, so final minus initial, that will basically give you 100. And that is going to give us 10,041.6 joules. And then the fourth energy, that is again a change of state. So we need latent heat now of vaporization. So the mass is still 24, but the latent heat of vaporization for the gas is what's the latent heat of vaporization? Let me get to check it out. Okay, the latent heat of vaporization for the ice, for me here is given as 40.7, but this value is in kilojoules per mole. Now remember the values which you are using here, the mass is in grams. You want the final answer to be in joules. This one is being given in kilojoules per mole. How can the mass, which is in grams, cancel with the mole? They can't cancel. So meaning that this latent heat which is given, I need to convert it also to the right unit. And how do you convert it? The answer is supposed to be in joules per gram, but this one is in kilojoules per mole. So we need to do that conversion. So I'm going to just multiply. We have got 4.07 kilojoules per mole. Okay, we are going to multiply. We are talking about water, remember. So we have got a mole down. I'm going to put a mole on top. And you know that 1 mole of water is equal to 18 grams. This is just from molar mass, like the molecular mass of water is 18 grams per mole, meaning that 1 mole of water is 18 grams. So the gram cancels with the gram, the mole also cancels with the mole. So the answer will just remain in kilojoules. To do away with the kilojoules, I'm just going to be able to multiply by 1000 the answer that I'm going to find. So that is going to give us 54,266.7 joules. And then the last energy, which is Q5, that is the energy required to raise the temperature, that is MC delta T. So the mass is still 24. Now specific capacity for the gas, in this case this is not water, is 2.01, and that will be now multiplied by the change in temperature. From 100 to 250, the change is 150. So the final answer we are going to get is 7,236 joules. So therefore, to find the heat energy now, the heat energy that is required for this process to happen, it's going to be a total of this value, and that will be 80,534 joules. That is going to be it. Is that okay?
Yes.
All right. So basically, this is what we get to consider. Now, let me just mention something.